Today, we're going to talk about something called Bayesian flow networks, or BFNs, and you're going to want to stick around for this because they represent a totally fundamental shift in how AI works, a shift that could honestly unlock the next huge wave of scientific discovery. So, let's start with the big promise, right? We're always hearing that AI is going to discover the next superdrug or build some revolutionary new material. But what if I told you that our most powerful AI models, the ones we see doing amazing things every day, have been held back by a hidden roadblock this whole time?
And yeah, it's true. For all their incredible power, the very models that generate those stunning images and write frankly amazing text, they have a kind of Achilles heel when it comes to the actual language of science.
Okay, so this is where we really get to the core of the problem. Your top AI models, think about the ones making art, they are absolute masters of continuous data. You know, like the smooth, seamless gradient of colors in a photograph. But the language of science? That's usually discrete. It's made of separate, distinct building blocks, like atoms in a molecule or letters in a gene sequence. Trying to use those image-generating AIs on scientific data, it's kind of like trying to paint a masterpiece using a bucket of Lego bricks. It just doesn't really work. So what do you do about that? Well, a team of researchers came up with a new idea. Instead of trying to force these old models to do something they weren't built for, they built a completely new one from the ground up, all based on this really powerful statistical idea called Bayesian inference. And here it is, the Bayesian flow network. The key difference is right there in the definition. It doesn't work by taking something perfect, breaking it, and then learning how to fix it. No. Instead, it generates something new by gradually refining a belief about what it should look like. And that, right there, is a really profound shift in thinking. To really get the difference, let's just quickly look at the old way. Diffusion models, which are amazing, take a perfect image, they blast it with noise until it's just static, and then they train an AI to learn how to reverse that entire process, to uncorrupt the data. BFNs do the exact opposite. They start with total uncertainty. Basically, a completely open mind. And then, step by step, the model gets little bits of information that allow it to build a more and more confident belief about the final thing it's trying to create. It's just a much more elegant solution that's a perfect fit for that building block nature of science. Probably the best way to wrap your head around this whole belief refinement thing is with a simple metaphor. Just think of it as a game of hints, a game between two players. And the paper itself uses this brilliant analogy. You've got a sender, let's call her Alice, who knows the secret piece of data. And then you have a receiver, Bob, whose job is to figure it out based on a series of noisy clues from Alice. So let's say Alice knows the exact 3D structure of a new molecule. That's our target, that's X. The BFN's job is to basically play the part of Bob, and using just hints, figure out exactly what X is. Okay, let's walk through the game. Step 1, Bob starts off knowing absolutely nothing, an open mind. Step 2, Alice sends him a really noisy, fuzzy hint. Step 3, Bob uses that hint to update his belief and make a first guess. Then, and this is clever, in step 4, a neural network looks at all of Bob's guesses and refines them to make sure they all make sense together. And finally, the whole process just repeats, with every new hint getting a little clearer until Bob's belief perfectly matches Alice's secret. Now, for those of you who want to see the math behind the magic, this table shows how that simple game maps directly onto the model's actual architecture. Every piece of the game, Bob's belief, Alice's hint, the update, it all has a precise mathematical role. It's this really rigorous foundation that makes BFNs so incredibly powerful. Okay, so that's the core idea, but this is where it gets really cool. Because this isn't just a theory, it's already being adapted into a whole family of specialized models, each one designed to tackle a specific, really complex scientific problem. This is where the rubber meets the road. First up is GeoBFN. Its whole mission is to generate stable, physically realistic 3D molecules. And this is unbelievably difficult, because you're not just picking atoms out of a hat. You're placing them in 3D space with incredible precision. A tiny, tiny change in one atom's position can make the entire molecule unstable and just fall apart. So how on earth does it do it? Well, GeoBFN is special because it handles both the type of atoms and their 3D positions at the exact same time. And most importantly, it understands a fundamental rule of physics. A water molecule is still a water molecule whether it's upside down, sideways, or backwards. By building in this deep understanding of rotation, it can design molecules that are not just new, but physically plausible. And that could massively speed up the search for new drugs. All right, next up, we've got CRISP-BFN, which is designed for the world of material science, specifically for generating crystals. And crystals have these repeating periodic structures, which present a totally new set of geometric puzzles for an AI to solve. So think about a crystal lattice, right? If you go off one edge, you're supposed to reappear on the opposite side, like in an old video game. Standard models just can't handle that. It's a huge blind spot. But CRISP-BFN has this clever solution for the wraparound problem, using some special math to treat the space like it's curved. This lets it generate perfect periodic crystals, the kind that could become our next generation batteries or solar panels, and it's setting new records for quality on major datasets.
But here's the kicker. It's not just about quality, it's about speed. And I mean game-changing speed. Compared to the older methods, CRISP-BFN is up to 200 times faster at generating new crystal structures. That's not just an improvement, that's a genuine revolution for how fast we can discover new materials. And the family just keeps on growing. There's a MOF-BFN for designing really complex materials that could be used for things like carbon capture. There's even a KG-BFN, which can build real-world engineering rules like this design has to have a specific volume, right into the generation process. It just goes to show you how flexible and powerful this core BFN idea really is.
So, when you put this all together, what does it really mean for the future? Where is this new BFN paradigm actually taking us? Here's the bottom line. The big takeaway is this. By shifting the whole process away from fixing corrupted data and toward believing in a structure built from hints, BFNs give us a single, powerful, and elegant framework. And it's one that works for all the different kinds of data that make up our world: discrete, continuous, and all the messy combinations in between. This unified approach is already opening up new frontiers in designing molecules and materials, which of course leaves us with one last really big question. Could BFNs be the key that finally allows AI to master the immense complexity of biology and to truly revolutionize fields like protein engineering? Only time is going to tell.